The question of whether we are the only living species in the universe is one of the greatest mysteries of science. For centuries, humanity has gazed at the night sky, wondering if other beings might also be staring back from distant worlds. Modern astronomy has revealed that the universe is not only vast, but also filled with countless opportunities for life to emerge. With more than 2 trillion galaxies, each holding billions of stars and planets, the probability that Earth is the sole cradle of life seems increasingly unlikely. This is Sleeping Universe, ready to make you fall asleep. Our Milky Way alone contains hundreds of billions of stars, and thanks to missions like Kepler and TESS, we now know that planets are more common than stars. Many of these planets orbit within the habitable zone, the region where temperatures allow liquid water to exist, a fundamental ingredient for life as we know it. Life on Earth offers a compelling blueprint for understanding how living systems might arise elsewhere. Billions of years ago, our planet was nothing more than a ball of molten rock. Yet, through chemistry and time, simple molecules formed complex organic compounds. In oceans rich with energy and minerals, these compounds assembled into molecules, which eventually gave rise to the first single-celled organisms. From that point, natural selection shaped the extraordinary diversity of life we see today. If such a transformation could occur here, it is reasonable to imagine it could happen on countless other worlds under the right conditions. Astrobiologists approach this question by studying both the requirements of life and the environments beyond Earth. Water, carbon-based chemistry, and stable energy sources are considered essential. Mars, Europa, Enceladus, and Titan worlds within our solar system already show signs that they may harbor some of these ingredients. Mars has evidence of ancient rivers and underground ice, while Europa and Enceladus are believed to contain vast subsurface oceans beneath icy crusts, warmed by internal heat. Titan, with its lakes of liquid methane, challenges our Earth-based assumptions by suggesting life could exist in forms very different from what we know beyond the solar system. Exoplanets provide an even more intriguing arena. Some orbit stars, similar to the Sun, and show sizes and compositions that hint at Earth-like conditions. Astronomers now search their atmospheres for biosignatures, gases such as oxygen, methane, or combinations of chemicals that are difficult to explain without life. The James Webb Space Telescope is beginning to make these searches possible, and in the coming decades, even more powerful observatories will sharpen our view. If we detect unusual atmospheric patterns, it could be the first hint that biology is at work light years away. But the question goes deeper than whether simple microbial life exists. If we are not the only living species, could there also be intelligent civilizations scattered among the stars? The Drake equation, developed in 1961, attempted to estimate how many advanced societies might exist in our galaxy. While many of its variables are uncertain, even conservative assumptions suggest the possibility of multiple civilizations. Yet, despite decades of listening through the search for extraterrestrial intelligence, SETI, no confirmed signals have reached us. This paradox, known as the Fermi paradox, highlights the tension between high probability and lack of evidence. Where are they, if they exist? Are they too far, too rare, or perhaps deliberately silent? Some scientists argue that intelligent life may be extremely rare, requiring not just habitable conditions, but also a delicate chain of evolutionary events. Others propose that civilizations rise and fall, and their signals may not overlap with our brief technological window. It is also possible that their methods of communication are so advanced that we fail to recognize them. Still, the absence of evidence is not evidence of absence. The universe is old, over 13 billion years, and humanity has only been listening for a fraction of a second on cosmic timescales. If we are not alone, the implications are profound. Even the discovery of microbial life beyond Earth would revolutionize biology, showing that life is not a rare fluke but a natural outcome of chemistry. It would suggest that the universe is filled with living species, each adapted to their unique environments. Intelligent civilizations, if they exist, would pose even greater questions about communication, cooperation, and survival. Would they share similar struggles as ours: climate, resources, technology, or would their paths be entirely different? If microbial life exists elsewhere, its discovery would not only reshape science, but also our perspective on existence. On Earth, microbes dominate nearly every environment, from boiling hot springs to deep ocean vents where sunlight never reaches. Their resilience shows that life does not need perfect Earth-like conditions to thrive. This means that if another planet or moon has liquid water, a source of energy, and essential elements like carbon, hydrogen, nitrogen, and phosphorus, life might naturally emerge. Imagine Europa's subsurface ocean, where hydrothermal vents could provide energy just as they do at Earth's ocean floors. Their entire ecosystems flourish without sunlight, relying on chemical reactions. If such ecosystems exist beyond Earth, they might represent the most common form of life in the universe, as more unseen, yet abundant. But what about intelligent life? Human intelligence evolved from billions of years of adaptation, survival, and chance. We are the result of countless evolutionary steps, from simple microbes to multicellular organisms, to mammals with complex brains. Intelligence, as we understand it, may not be inevitable. It could be a rare byproduct of evolution rather than a guaranteed outcome. Still, with billions of planets in our galaxy alone, even rare events could occur many times. If other intelligent species exist, they might look nothing like us. Evolution would shape them based on their environment. Creatures of water worlds could develop sonar-like communication, while those on high-gravity planets might evolve shorter, sturdier bodies. Their intelligence might be expressed not in technology but in ways we cannot yet imagine, perhaps through biology itself, or through communication we have no means of detecting. The Fermi paradox remains one of the biggest puzzles. If intelligent species exist, why haven't we seen evidence of them? One explanation is distance. The universe is so vast that even light, the fastest traveler, takes thousands or millions of years to move between stars. A signal from another civilization might still be on its way to us, or perhaps it passed by long before humans learned to listen. Another explanation is survival. Civilizations may rise, flourish, and collapse in relatively short spans compared to cosmic time. Humanity has only been using radio technology for just over a century. In that small window, our signals have barely reached nearby stars. If other civilizations follow similar paths, the overlap between their signals and our listening might be vanishingly small. There is also the possibility that advanced civilizations choose not to broadcast. Some scientists suggest that broadcasting one's existence could be dangerous, as it reveals location to unknown others. Others imagine that advanced societies may focus on inward development, creating technologies beyond our understanding but not directed outward. For instance, they could use quantum communication, neutrinos, or other methods invisible to our instruments. To us, Their silence may seem like absence, but in reality, they might simply be beyond our detection. Despite this, humanity continues the search. Projects like CTI listen for radio signals, scanning the skies for patterns that cannot be explained by natural sources. New approaches look for technosignatures, such as unusual heat emissions from large structures or atmospheric compositions that suggest industrial activity. If one day we detect such a signature, it would confirm that we are not the only species capable of reshaping our world. Even if contact never occurs, just knowing they exist would change everything. The psychological and cultural impacts would be enormous. Throughout history, each major scientific discovery, heliocentrism, evolution, relativity has transformed our understanding of humanity's place in the universe. The discovery of extraterrestrial life would be no different. Religions, philosophies, and cultures would all be challenged to reinterpret humanity's role. Are we special, or simply one species among countless others? Would we fear them, admire them, or seek to learn from them? The answer would depend not only on what kind of life we find, but also on how prepared humanity is to accept it. If microbial life is discovered, it would fuel a new age of exploration. Missions would focus on sampling alien biochemistry, comparing it to Earth's life, and asking whether life across the universe shares a common origin. Some scientists even suggest panspermia, the idea that life can travel between planets on asteroids or comets. If microbes on Mars or Europa share DNA-like chemistry with us, it could mean life is more interconnected than we thought. On the other hand, if alien microbes use entirely different molecular systems, it would prove that life has many possible solutions. Either outcome would expand biology into a truly universal science. If intelligent life is found, the stakes rise higher. Communication would be humanity's first challenge. Our radio signals might take decades or centuries to reach them, and their replies would take just as long. Real-time dialogue may be impossible, so we would rely on patience and long-term commitment. The content of such communication could redefine science, technology, and even our ethics. Perhaps they would share knowledge of energy sources we cannot yet grasp, or medical insights that could extend life. Yet, there is also risk. Contact could reveal differences so profound that misunderstandings are inevitable. Even without hostility, the cultural shock might destabilize societies. Governments would face questions of secrecy versus transparency, and citizens would demand to know if we were safe. History suggests that encounters between civilizations at different levels of development often favor the more advanced, sometimes with devastating consequences. This raises the possibility that intelligent life, if it exists, avoids us deliberately. Known as the zoo hypothesis, it suggests they might observe us without contact, allowing us to develop without interference, much as humans might observe animals in a reserve. Whether this is comforting or unsettling depends on perspective. In any case, the search for other species in the universe is also a search for understanding ourselves. By asking if we are alone, we confront what it means to be human. If life is common, then the universe is filled with diversity and possibility. If life is rare, then our responsibility to protect and sustain it becomes even greater. The fragility of Earth, a small blue dot in a vast void, reminds us that life here may be unique, that knowledge alone should inspire us to care for our world and strive for a future where humanity can endure long enough to discover whether others are truly out there. The exploration continues with technology as our guide. Each new telescope, probe, and mission pushes the boundaries. The James Webb Space Telescope peers into exoplanet atmospheres. The Perseverance rover drills into Martian rocks in search of ancient biosignatures. Future missions to Europa and Enceladus aim to pierce their icy shells and sample hidden oceans. Each discovery, no matter how small, adds to the story. Perhaps the first evidence will not come in the form of alien civilizations, but as a faint chemical trace in the air of a distant planet, or as fossilized microbes locked in Martian stone. And yet, even without proof, the logic of probability is powerful. If the universe holds trillions of planets, and if life can arise from chemistry under the right conditions, then it seems unlikely that Earth is alone. The real question may not be if other living species exist, but when we will find them. Humanity stands at the threshold of that answer. For the first time in history, we have the tools to seek life beyond our world. Whether we find microbes in our solar system or signals from the stars, the discovery will mark a turning point in our story as a species. Asterisk, when we think about the possibility of not being the only living species in the universe, we must also examine the deep history of our own planet to see how life managed to persist against incredible odds. Earth's story is one of resilience. The first microbes emerged more than 3.5 billion years ago, and since then, our planet has endured asteroid impacts, global ice ages, massive volcanic eruptions, and dramatic climate shifts. Yet, life has not only survived but thrived, diversifying into millions of species. This resilience demonstrates that once life begins, it is extraordinarily difficult to extinguish entirely. Such durability suggests that if life takes hold elsewhere in the universe, it too may be capable of adapting and surviving for billions of years under conditions that might seem hostile to us. One of the strongest arguments in favor of extraterrestrial life comes from the concept known as the mediocrity principle. This principle argues that Earth and humanity are not special or unique in the grand scheme of the cosmos. Instead, we are typical, and what has happened here is likely to happen elsewhere. Our Sun is an average star in an average galaxy, and our planet is not exceptional in its makeup. If life arose here under ordinary circumstances, it is rational to think that similar processes have occurred in countless other places. To assume that Earth alone produced life is to assume that we are an exception in a universe built on probabilities. Science teaches us to be cautious of such assumptions. The search for life often focuses on worlds similar to Earth, but recent discoveries remind us that life can exist in unexpected places. On Earth, extremophiles organisms that survive under extreme conditions have been found thriving in environments once considered uninhabitable. Bacteria live in boiling hot springs, fungi endure high radiation levels inside nuclear reactors, and microbes have been found surviving in the upper atmosphere where conditions resemble those of Mars. Some organisms, such as tardigrades, can even survive in the vacuum of space for limited periods. These findings challenge the idea that life needs mild Earth-like conditions. Instead, they suggest that the definition of habitable is much broader than once believed. If life can endure the extremes of our planet, then alien life may thrive in forms and habitats we cannot yet imagine. Our solar system provides several compelling candidates for such life. Mars, once thought barren, continues to reveal evidence of ancient rivers, lakes, and possibly even an ocean. Although its surface is dry and exposed to harsh radiation today, scientists believe microbial life may have existed when Mars was warmer and wetter billions of years ago. If microbes ever lived there, some may still persist underground, protected from radiation and sustained by subsurface ice and minerals. Discovering even fossilized remains of Martian microbes would prove that life emerged twice within a single solar system, dramatically increasing the likelihood that it exists elsewhere. Europa and Enceladus, moons of Jupiter and Saturn, represent another exciting frontier. Beneath their icy shells lie vast oceans of liquid water, kept warm by tidal forces generated by their parent planets. On Earth, deep-sea hydrothermal vents provide ecosystems rich in life despite complete darkness. Powered by chemical energy instead of sunlight, similar conditions may exist beneath the ice of these moons. The geysers of Enceladus, which shoot water vapor and organic compounds into space, already suggest the potential for habitability. If a future mission samples these plumes and finds even simple biological molecules, it would be one of the most important discoveries in human history. Further afield, exoplanets continue to capture attention. Astronomers categorize them as rocky, gaseous, icy, or ocean worlds. Some are super-Earths, larger than our planet but smaller than Neptune, which may have stable surfaces and thick atmospheres. Others orbit in the habitable zones of their stars, where conditions might allow liquid water. The search for biosignatures, atmospheric gases, or patterns that suggest biological activities intensifying. Oxygen, combined with methane, for example, is difficult to maintain without life constantly replenishing it. Detecting such a pattern in an exoplanet's atmosphere would be strong evidence of alien biology, even if we never see the organisms themselves. The challenges, however, remain enormous. Distances in space are so vast that even the closest stars are light years away. This means direct exploration is limited to our solar system for now. Detecting life beyond requires interpreting faint signals, distinguishing between biological and non-biological sources. For instance, methane can be produced both by microbes and by geological processes. Sorting out such ambiguity demands careful, patient science. Yet, step by step, technology is improving. The James Webb Space Telescope has already begun probing exoplanet atmospheres, and future telescopes will sharpen our ability to detect biosignatures. Humanity is building the tools that could answer the question within our lifetimes. The implications of discovering another living species, even microbial, go far beyond science. It would challenge deep-rooted human assumptions about uniqueness. Throughout history, major discoveries have reshaped our worldview. When Copernicus showed that Earth was not the center of the universe, it shifted humanity's place in the cosmos. Darwin's theory of evolution connected us to all other life on Earth. Finding extraterrestrial life would be the next great shift, showing that biology is a universal phenomenon, not a rare accident. If we take the possibility of intelligent life into account, the implications expand even further. The Drake equation, though uncertain, provides a framework to think about the number of civilizations in our galaxy. If life emerges easily and intelligence evolves frequently, then the galaxy could be full of civilizations. But if intelligence is rare, we may be one of only a few. This uncertainty fuels both hope and caution. Contact with another intelligent species could provide answers to questions about survival, cooperation, and technology. Yet, it could also pose risks. Civilizations at different technological levels often face difficulties in understanding each other, and the possibility of unintended consequences cannot be ignored. Some scientists suggest that the very reason we have not found others is because advanced civilizations do not reveal themselves. The Great Filter hypothesis proposes that there are difficult stages in evolution that most life cannot pass, whether the origin of life, the development of intelligence, or the ability to survive technological advancement. If humanity has already passed the filter, then perhaps we are among the few to succeed. If the filter lies ahead, however, it warns of challenges that could threaten our long-term survival. In either case, the idea that we may not be alone forces us to confront the fragility of our own existence. Ethical questions also arise. How should humanity respond if alien life is discovered? With microbes, the concern is planetary protection, avoiding contamination both ways. Bringing alien microbes to Earth could pose biological risks, while contaminating other worlds with Earth life could erase pristine environments. With intelligent life, the stakes are even higher. Would we have the right to interfere, to send messages, or to attempt contact? International agreements like the Outer Space Treaty already emphasize the importance of preserving celestial bodies, but they were written before the real possibility of discovering life seemed so near. Future generations may need entirely new ethical frameworks to guide humanity's interactions with alien species. Despite uncertainties, the search for life in the universe is one of the most unifying endeavors in science. It brings together astronomers, biologists, chemists, engineers, and philosophers. It fuels missions to explore distant planets, inspires the development of powerful telescopes, and sparks curiosity in millions of people worldwide. At its core, the search reflects our desire to understand not only the cosmos, but ourselves. Whether we find microbes under Martian soil, alien plankton drifting in Europa's ocean, or signals from a distant civilization, each discovery will teach us something new about the nature of life. In the end, the question of whether we are alone may be less about finding others and more about recognizing our shared journey. Life on Earth represents a fragile, precious phenomenon, and the search for others reminds us of the importance of protecting it. Even if the universe is full of living species, the vast distances mean we may never meet them. That makes our responsibility to sustain and cherish our own planet even greater. But the search itself, driven by science, curiosity, and wonder, will continue to push us forward, expanding our horizons and deepening our understanding of the cosmos we call home. As scientists continue their exploration of life's possibilities in the cosmos, one key concept emerges again and again: convergence. On Earth, life has repeatedly evolved similar solutions to survival problems, even in unrelated species. Wings evolved in birds, bats, and insects independently. Eyes developed in octopuses and mammals with very different evolutionary lineages. This phenomenon of convergent evolution suggests that given similar pressures, life tends to find similar paths. If this principle holds true across the universe, then alien life, though shaped by different environments, might not be wholly unfamiliar. It could possess recognizable features such as eyes for detecting light, appendages for movement, or communication systems, even if their forms are unlike anything on Earth. This line of reasoning gives weight to the idea that intelligence itself could also be a convergent trait. While intelligence on Earth is most associated with humans, other species demonstrate advanced cognition. Dolphins with their complex social structures, crows with their problem-solving skills, and octopuses with remarkable learning abilities. Intelligence appears to be a valuable survival adaptation in diverse environments. Thus, even though it may be rare, The possibility that evolution produces intelligent species elsewhere is not far-fetched. If so, we might not only share the universe with other life, but with other minds capable of questioning their own existence, just as we do. Still, the silence of the stars remains. Despite the statistical likelihood of extraterrestrial civilizations, no confirmed contact has been made. The Fermi paradox hangs like a shadow over our curiosity. Solutions to this paradox vary. Some argue that advanced civilizations may be too far apart in time and space to overlap. Others suggest that civilizations may destroy themselves before reaching the stage of interstellar communication. Nuclear war, climate collapse, or uncontrolled artificial intelligence could all threaten survival. In this sense, the absence of signals could be a warning, a mirror reflecting our own vulnerabilities. Another possibility is that communication is happening, but we are not equipped to detect it. Our current methods rely heavily on radio waves, but an advanced civilization might use technologies far beyond our comprehension. Imagine communication through neutrinos, quantum entanglement, or methods that bypass space-time constraints altogether. To such beings, our radio telescopes might appear as primitive as smoke signals. If this is the case, then the universe could be alive with communication we simply cannot perceive. Beyond technology, cultural differences could explain the silence. Human curiosity drives us to search and reach out, but another species might not share this instinct. Perhaps they value secrecy, fearing the dangers of contact, or perhaps they view us as we view and are aware of our existence, but uninterested in direct communication. Such scenarios force us to rethink our assumptions. We often imagine aliens as beings who think like us, but the truth may be that their motivations, priorities, and perceptions are completely alien in every sense of the word. If one day we do receive a signal, even a faint one, the consequences would ripple across every aspect of human society. The first step would be verification. Scientists would need to rule out natural phenomena and ensure the signal was not a false alarm. Only then could the world absorb the truth that we are not alone. Governments, scientists, religious leaders, and ordinary people would all respond differently. Some might rejoice at the confirmation of cosmic neighbors, while others might feel fear, uncertainty, or even denial. Human history shows that great paradigm shifts are rarely smooth. The discovery of extraterrestrial life would be no exception. The cultural impact could be transformative. Religions might adapt by incorporating the idea of multiple creations, or expanding their theological frameworks to include extraterrestrial beings. Philosophers would debate the meaning of humanity's place in a universe populated by others. Artists and writers would find endless inspiration, and society at large might experience both awe and humility. Knowing that other living species exist could unify humanity, highlighting our shared identity as Earthlings rather than dividing us by nation or culture. At the same time, it could introduce new anxieties about survival, security, and competition. The scientific community is already preparing for this possibility. Organizations such as the SETI Institute and International Space Agencies have drafted protocols for how to respond if contact occurs. These protocols emphasize transparency, verification, and global cooperation. Yet, no plan can fully anticipate the complexities of first contact. Would we attempt to reply immediately? What message would we send, and who would decide its content? Even the simplest response could carry risks, as revealing our location might expose us to unknown dangers. Still, the urge to communicate would likely prove irresistible. Humanity has always sought connection, and the chance to speak across the stars would be too powerful to ignore. If, on the other hand, the first evidence of extraterrestrial life comes in the form of microbes rather than messages, the implications would still be staggering. Biologists would study alien microbes to understand their chemistry, metabolism, and evolutionary potential. Do they use DNA or some entirely different molecule as their genetic code? Do they rely on water or another solvent like methane or ammonia? Each answer would expand our understanding of biology and demonstrate that life can take multiple paths. Such discoveries would influence medicine, technology, and even our search for origins. If alien life is fundamentally different from ours, it would prove that the universe is not constrained to one blueprint. If it is similar, it could suggest that all life shares a common ancestry, perhaps spread by panspermia. The panspermia hypothesis holds that life may not have originated independently on every world where it is found, but rather spread between planets via comets, asteroids, or interstellar dust. Microbes are surprisingly resilient, and experiments have shown that some can survive the conditions of space. If panspermia is true, then Earth itself may be seeded from elsewhere, making us cosmic immigrants. In that case, the search for life is not just about finding others, but about tracing our own distant relatives across the galaxy. Looking to the future, the tools at humanity's disposal are becoming increasingly powerful. Upcoming missions like Europa Clipper and Dragonfly to Titan are designed specifically to probe for signs of habitability and potential biosignatures. Giant, ground-based telescopes will peer into exoplanet atmospheres with unprecedented detail. Private companies and international coalitions are planning more ambitious space missions, and breakthroughs in propulsion may one day allow robotic probes to journey to the nearest stars. As our reach expands, so does the possibility of making first contact, whether with microbes in our neighborhood or with civilizations far away. But perhaps the most profound aspect of this search is what it reveals about us. The longing to know if we are alone reflects something deeply human. We are a species driven by curiosity, by the need to understand our place in the universe. This quest unites science, philosophy, and imagination. Even if we never find others, the act of searching gives meaning. It reminds us of the fragility of life, the beauty of our world, and the importance of stewardship. It pushes us to ask better questions, to build better tools, and to dream beyond the boundaries of our planet. In the end, the question of whether we are the only living species in the universe may never have a definitive answer. The cosmos is vast, and our existence within it brief, but the evidence continues to build that life, at least in simple forms, may be widespread. With each discovery of a new exoplanet, with each detection of organic molecules, with each mission to icy moons, we come closer to an answer. Perhaps in our lifetimes, perhaps centuries from now, humanity will finally know. And when that day comes, whether we find neighbors across the galaxy or only microbes beneath the ice of Europa, the universe will never feel the same again. If we accept that the universe is filled with billions of planets, many of them rocky and potentially habitable, then the natural next question is not simply if life exists elsewhere, but how common it might be. This shifts the discussion from philosophy to probability. Astronomers now estimate that in the Milky Way alone, there could be as many as 40 billion Earth-sized planets orbiting in habitable zones around their stars. If even a fraction of these worlds host life, the galaxy could be teeming with living species. This doesn't guarantee that all such planets are inhabited, but it emphasizes that Earth cannot be the only cradle of biology. The challenge lies in the immense diversity of planetary conditions. Some worlds may resemble Earth, with oceans, atmospheres, and continents. Others may be water worlds entirely covered in oceans, or desert planets with scarce moisture. Some may orbit red dwarf stars, which are far more common than stars like our Sun. These stars burn cooler and longer, potentially giving their planets billions of extra years of stability. Yet, they also produce violent stellar flares, which could strip atmospheres and bathe planets in radiation. Whether life can adapt to such extremes remains uncertain. But if extremophiles on Earth are any indication, biology has a way of finding solutions. One of the most fascinating aspects of this exploration is how much it forces us to expand our imagination while remaining grounded in evidence. For centuries, humans imagined alien species in forms familiar to Earth, often humanoid, with 2 arms, 2 legs, and a face. But science teaches us that evolution is not bound to human forms. On a high-gravity world, creatures might evolve low, sturdy bodies. On a planet with thick, cloudy atmospheres, species might develop sonar-like senses instead of eyes. In methane-rich environments, life might use chemistry entirely alien to us, perhaps building cells from hydrocarbons instead of water. What unites all these possibilities is not their resemblance to Earth life, but the universality of adaptation. Life, wherever it appears, will adapt to its environment, finding ways to survive within the constraints of physics and chemistry. Yet, the search for extraterrestrial species is not only about finding life itself, but also about confronting the profound silence of the cosmos. Decades of scanning the skies have yielded no confirmed signals from intelligent civilizations. This silence forces us to wrestle with difficult possibilities. It could mean that life is common, but intelligence is rare. It could mean that intelligent life often destroys itself before it can reach across the stars. Or it could mean that the universe is buzzing with activity, but we lack the means to detect it. Each possibility carries lessons for humanity. If intelligence is rare, then our responsibility to preserve it becomes enormous. If civilizations often collapse, then we must take our survival seriously. And if the universe is alive with communication beyond our detection, then we are reminded of how young and primitive we still are on the cosmic scale. Despite this silence, scientists remain optimistic because evidence continues to mount in other ways. Organic molecules, the building blocks of life, have been found on comets, in interstellar clouds, and even on Mars. These discoveries suggest that the ingredients for life are widespread. If chemistry can produce life here, and the raw materials are everywhere, then the leap from chemistry to biology may not be rare at all. In fact, it may be the natural outcome of physics and chemistry given enough time. This is why many researchers believe that the discovery of even microbial life beyond Earth is inevitable. The question is not if, but when, that the social consequences of that discovery would depend on what we find. Microbial life would be less threatening than intelligent civilizations, but still revolutionary. It would tell us that biology is not unique to Earth, and that the cosmos is filled with living processes. This could inspire a new scientific renaissance, expanding biology into a universal science. On the other hand, intelligent life would be far more complex. If we were to receive a signal, the entire world would stop to listen. Every culture, every religion, every government would scramble to interpret the meaning. Some would see it as confirmation of beliefs, others as a challenge to them. Economies might shift as priorities change, and politics would be forced into a global perspective. After all, The existence of another intelligent species would remind us that our divisions here on Earth are trivial compared to the vastness of the universe. Still, the risks cannot be ignored. History teaches us that encounters between civilizations of different technological levels often lead to exploitation, misunderstanding, or even collapse of the less advanced society. This raises a sobering question. Should humanity even attempt to broadcast our presence? Some scientists warn against it, arguing that to announce ourselves to the galaxy is to invite unknown risks. Others believe that any species capable of interstellar travel would already know of our existence. Given that Earth's atmosphere has contained biosignatures like oxygen for billions of years, in either case, the decision to actively reach out or to remain silent is not a trivial one. It is a decision that could shape the future of our species, beyond the scientific and cultural impacts. The discovery of other living species would also transform how we see ourselves. The famous image of Earth as a pale blue dot already shifted human perspective, showing our planet as a fragile speck in an infinite void. Knowing that life exists elsewhere would deepen that perspective. It would remind us that we are part of a greater biological community spread across the cosmos. For many, this would be a source of comforter reassurance that we are not alone in the vast dark. For others, it might provoke fear or existential dread. But either way, it would change humanity forever. The journey to that discovery is already underway. Mars missions continue to search for traces of ancient life. Europa Clipper will soon investigate the icy ocean moon of Jupiter, while Dragonfly will explore Titan's methane-rich environment. Telescopes are scanning distant exoplanets for biosignatures, while SETI and related projects keep their ears open for signals. Each step may bring us closer to an answer. It is possible that the first evidence will be subtler, strange chemical imbalance in an exoplanet's atmosphere, or a faint, unexplained radio pattern. Or it could be dramatic, like fossilized microbes on Mars, or an unmistakable message from the stars. The timeline is uncertain, but the trajectory of discovery is clear. Humanity is edging closer to answering the question of whether we are alone, even if the answer takes centuries. The very act of searching matters. It pushes us to build better technologies, to ask deeper questions, and to think beyond ourselves. It fuels cooperation across nations and disciplines, reminding us that the quest is bigger than any one country or generation. It inspires wonder in young minds and encourages a sense of humility and unity. After all, if the universe is indeed filled with other living species, then humanity is part of something far greater than itself. And if we are alone, then our responsibility to cherish and preserve life on Earth is even more profound, for we would represent the only known spark of biology in the entire cosmos. Asterisk in either case. The search for life beyond Earth is not just a scientific pursuit, it is a human one. It speaks to our deepest curiosity, our fears, our hopes, and our need for connection. To look up at the stars and ask, "Are we alone?" is to express what it means to be human. The answer, when it comes, will echo not only in science, but in every corner of our existence. As humanity probes the cosmos in search of life, one of the most profound insights comes from comparing the conditions of other worlds to those of early Earth. Our planet did not begin as a haven for life. It started as a molten sphere bombarded by asteroids, with a volatile atmosphere and oceans forming slowly over millions of years. Yet, life emerged. This suggests that, given enough time, the right chemistry, and some stability, life may arise in environments that seem hostile at first glance. If life could originate under these conditions on Earth, then planets or moons with similar characteristics elsewhere might have done the same. The universe may be less barren than our imaginations often assume. Extremophiles on Earth illustrate the surprising resilience of life. Organisms survive in boiling acid springs, at the crushing pressures of deep ocean trenches, in frozen Antarctic lakes, and even exposed to near-vacuum conditions in space. These examples expand the boundaries of what scientists consider habitable. A planet does not need to resemble modern Earth perfectly to host life. Europa's subsurface ocean, warmed by tidal heating from Jupiter's gravitational pull, may harbor microbial ecosystems thriving without sunlight. Enceladus ejects plumes of water and organic molecules into space, offering a rare opportunity to sample potential extraterrestrial life without landing. Even Titan, with its lakes of methane and ethane, challenges our understanding by suggesting that life could exist in forms fundamentally different from water-based organisms. The adaptability of life on Earth gives reason to believe that wherever suitable conditions exist, biology may have taken root, that the discovery of exoplanets further heightens the probability of life elsewhere. Thousands of planets orbiting other stars have been confirmed, many of them in the habitable zones where temperatures allow liquid water to exist. Some of these exoplanets are remarkably similar to Earth in size and composition, while others are super-Earths or ocean worlds, presenting possibilities beyond our imagination. Astronomers now search their atmospheres for biosignatures, chemical markers such as oxygen, methane, or other compounds that could indicate life. The combination of observational astronomy, spectroscopy, and theoretical modeling is gradually turning science fiction into scientific plausibility. Every detection of a potentially habitable exoplanet reinforces the idea that Earth may not be unique. Yet, the question of intelligent life adds another layer of complexity. Human intelligence emerged from a long, contingent chain of evolutionary events. While intelligence provided clear advantages, it was by no means inevitable. Other intelligent species on Earth, such as dolphins and crows, demonstrate advanced problem-solving, but have not developed technological civilizations. Extrapolating this to the cosmos, it is possible that life is common, but intelligence is rare. The Drake equation, despite its uncertainties, provides a framework for considering the factors involved: the rate of star formation, the fraction of stars with planets, the fraction of planets where life arises, and the likelihood of intelligent civilizations. Even conservative estimates suggest that intelligent species could exist elsewhere. But whether they overlap in time and space with humanity is another matter entirely. This leads directly to the enduring mystery known as the Fermi paradox. If intelligent life is probable, why have we not observed any evidence? The solutions proposed are diverse and thought-provoking. Some suggest that civilizations self-destruct before they can reach the stage of interstellar communication, succumbing to environmental collapse, technological catastrophes, or internal conflict. Others posit that advanced civilizations deliberately avoid contact with less developed species, adhering to a cosmic prime directive to allow natural evolution to proceed. Still others speculate that alien technology exists, but operates in ways we cannot detect. Communication may occur through mediums beyond human comprehension, such as neutrino streams, quantum entanglement, or signals embedded in cosmic radiation. In any case, the silence challenges us to confront our assumptions about life and intelligence. The potential discovery of life, whether microbial or intelligent, raises profound ethical and philosophical questions. If microbes are found on Mars or Europa, humanity must decide how to study them without contamination. Planetary protection protocols are designed to prevent the transfer of Earth life to alien ecosystems and vice versa, ensuring that we do not destroy or inadvertently harm extraterrestrial biology. These precautions underscore the responsibility inherent in the search. Discovering life is not merely a scientific achievement, but also a moral undertaking. The same responsibility multiplies exponentially if intelligent life is detected. How would we communicate? What rights do extraterrestrial beings have? Would we be obligated to avoid interference, even if their existence could accelerate our own technological advancement? Cultural implications of discovery would be immense. Religions, philosophies, and social structures would confront new paradigms. Humanity has often defined itself in isolation, as the pinnacle of creation, as unique in the universe, or as the center of cosmic significance. Evidence of other living species, particularly intelligent ones, would force a re-evaluation of these assumptions. Religions might reinterpret doctrines. Philosophers would debate the nature of consciousness and morality, and societies could either unify under a shared cosmic perspective or fracture under fear and uncertainty. The psychological impact alone could be transformative. Knowing that we are not alone might inspire wonder, humility, and cooperation, or it could provoke anxiety, xenophobia, or existential dread. Technological considerations also emerge in the search for extraterrestrial intelligence. Humanity has only recently developed the ability to send and receive signals across interstellar distances. Radio waves, once cutting edge, may already be obsolete for advanced civilizations. This mismatch in technology might explain part of the Fermi paradox. We are listening with tools that are too primitive to detect signals from highly developed societies. Future technologies, perhaps employing quantum communication or advanced sensing methods, may finally reveal what has eluded us for decades. Until then, the search is a blend of patience, ingenuity, and imagination. Constrained by the limitations of our current capabilities, but fueled by a boundless curiosity, scientific research also emphasizes the diversity of potential life forms. While we often focus on carbon-based life in watery environments, alternative chemistries are theoretically possible. Life might exist in solvents like ammonia or methane, with molecular structures fundamentally different from DNA and proteins. Titan's lakes of liquid methane and ethane hint at such possibilities. If biology can arise in multiple chemical frameworks, then the universe could host forms of life entirely unlike anything on Earth, expanding the scope of what it means to be alive. Our challenge is to recognize life even when it does not resemble our terrestrial experience. Panspermia. The hypothesis that life can spread between planets and even solar systems via comets and asteroids further complicates the picture. If Earth life originated elsewhere, or if Martian microbes share a common ancestry with Earth organisms, then the universe may be a network of biological exchange. This would mean that life is not a rare accident, but a cosmic process, linking planets and systems in a web of living matter. Such a perspective transforms the search from a local inquiry to a galactic-scale investigation, asking not merely where life exists, but how it travels, evolves, and persists. The psychological dimension of this search cannot be overstated. Humanity's desire to know if we are alone reflects a fundamental aspect of our cognition. We are not satisfied with simply existing. We seek meaning, connection, and context. Gazing at the night sky, we wonder whether there is someone else, pondering the same question, somewhere across the vast cosmic ocean. This curiosity drives science, motivates exploration, and shapes culture. It explains why billions are invested in telescopes, space probes, and interstellar research programs. The question of alien life is, at its core, a question about ourselves. Who are we, and what is our place in the universe? Even the absence of evidence carries profound lessons. The lack of detected intelligent signals may indicate that civilizations are fragile, transient, or isolated. This serves as both a cautionary tale and a call to action. Humanity faces existential risks from climate change, nuclear weapons, and technological upheaval. Observing the potential fragility of intelligent life elsewhere might encourage us to safeguard our own. We may be among the first civilizations to achieve interstellar awareness, and with that awareness comes responsibility. Survival is not guaranteed, but the endeavor to persist is what defines a species capable of pondering the cosmos. As we explore further, the role of technology becomes increasingly central. Space telescopes, like James Webb, and future projects, such as the Extremely Large Telescope, aim to probe exoplanet atmospheres for signs of life. Robotic missions to Mars, Europa, and Enceladus will search for evidence of past or present organisms. Artificial intelligence is being integrated into observational systems to detect subtle patterns humans might miss. Each advance increases the probability of discovery and narrows the window of uncertainty. The tools we develop today will shape humanity's understanding of life for generations to come. In the end, the search for other living species is as much a journey of the mind as it is of science. It challenges our assumptions, stretches our imagination, and forces us to confront profound questions about survival, ethics, and identity. Whether we discover microbes in an icy ocean, complex organisms on a distant exoplanet, or intelligent civilizations reaching across the stars, each discovery will redefine humanity's place in the cosmos. Even if we remain alone, the act of searching imparts knowledge, humility, and purpose. It reminds us that life on Earth, fragile and finite, is precious, and that our stewardship of it carries immense significance. The universe, vast and ancient, may be filled with life. It may harbor beings who see the cosmos in ways we cannot comprehend, who survive under conditions we would consider hostile, and whose intelligence manifests in forms beyond our imagination. Whether microbial, complex, or intelligent, such life would demonstrate that Earth is not an isolated island, but part of a greater living tapestry. Humanity's journey to discover these species is ongoing, driven by curiosity, technology, and the timeless desire to understand our place in existence. The potential existence of other life forms in the universe forces humanity to rethink what it means to be alive. On Earth, life is astonishingly diverse. From single-celled bacteria to complex multicellular organisms, biology has adapted to nearly every niche imaginable. Life has survived asteroid impacts, ice ages, volcanic eruptions, and dramatic climate changes, constantly evolving, diversifying, and thriving. This resilience suggests that life, once it begins, can endure extreme conditions over billions of years. If life can arise and persist under such challenges on Earth, then planets and moons with different, perhaps harsher, environments may still host organisms that have similarly adapted. The discovery of extremophiles, organisms that thrive in environments once thought uninhabitable, demonstrates that life does not require the perfect conditions that humans once assumed. Microbes live in boiling hot springs, deep within Antarctic ice, in acidic lakes, and even in the high radiation environment of space. Some survive prolonged desiccation, extreme temperatures, or intense pressure. This extraordinary adaptability suggests that life could emerge and flourish in forms completely alien to human expectations. Oceans beneath the ice of Europa and Enceladus may harbor microbial ecosystems, sustained not by sunlight but by chemical energy produced by tidal heating or hydrothermal vents. On Titan, life may exist in methane or ethane lakes, relying on biochemistry that is completely unfamiliar to Earth-based life. The diversity of possibilities forces scientists to broaden their definitions of habitability and reconsider the range of environments in which life could thrive. Exoplanet research adds another layer of depth to the search for extraterrestrial life. Thousands of planets have been discovered orbiting stars beyond our solar system, many of them in habitable zones where temperatures allow liquid water to exist. Some are rocky Earth-sized worlds, while others are super-Earths, or ocean worlds. With the development of advanced telescopes capable of analyzing planetary atmospheres, scientists are searching for biosignatures, chemical markers that indicate the presence of life. Oxygen and methane in an atmosphere, for example, may suggest biological activity, as these gases would otherwise react and disappear over time. The discovery of a planet with a clear biosignature would be one of the most significant scientific achievements in history, confirming that life exists beyond Earth. Intelligence, however, presents a different set of questions. Human intelligence, capable of creating technology, art, and complex societies, is not inevitable in evolution. Many Earth species exhibit remarkable cognitive abilities without developing civilizations. Dolphins, crows, and octopuses display problem-solving skills and social intelligence, yet none have developed technology comparable to humans. This suggests that while life may be common, intelligence and, particularly technological intelligence, could be rare. Even if intelligent species exist elsewhere, they may be at different stages of development, isolated from one another by vast distances and timescales. The Fermi paradox, the apparent contradiction between the high probability of intelligent life and the lack of evidence for it, remains a central challenge in astrobiology. Several explanations for the Fermi paradox exist. Some propose that intelligent civilizations tend to self-destruct before achieving interstellar communication, succumbing to environmental collapse, warfare, or technological catastrophes. Others suggest that civilizations deliberately avoid contact with less advanced species, allowing them to evolve naturally. Alternatively, advanced civilizations may communicate using technologies or methods beyond human comprehension, such as neutrino-based signals, quantum entanglement, or other channels we have yet to discover. Each possibility carries profound implications for humanity, challenging assumptions about survival, technology, and our place in the universe. The potential discovery of extraterrestrial life, microbial or intelligent, raises both scientific and ethical questions. Planetary protection protocols are designed to prevent contamination between Earth and other celestial bodies, ensuring that alien ecosystems are preserved and that Earth is not exposed to unknown pathogens. If intelligent life is detected, the ethical stakes are even higher. Decisions regarding communication, interaction, and potential intervention would require unprecedented global cooperation and foresight. Humanity would be forced to consider the rights and welfare of alien species, as well as the potential consequences of our own actions. The search for life is therefore not only scientific, but moral, emphasizing responsibility alongside curiosity. Cultural implications would be equally profound. Religions, philosophies, and societies have long defined humanity as unique. Yet the discovery of extraterrestrial life would challenge that perspective. Some may integrate the existence of aliens into theological frameworks, while others might struggle to reconcile traditional beliefs with new realities. Philosophers would debate the nature of consciousness, ethics, and identity in a universe populated by multiple intelligent species. Social structures could shift toward a more unified global perspective, emphasizing humanity's role as a single species on a fragile planet. Alternatively, fear of the unknown might provoke division and conflict. The psychological and societal impact of discovering life elsewhere cannot be underestimated. Technology will play a critical role in the continued search for life. Advanced telescopes and space probes are designed to analyze planetary surfaces, atmospheres, and potential biosignatures with unprecedented precision. Robotic missions to Mars, Europa, Enceladus, and Titan are planned or underway, each targeting environments where life might exist. Artificial intelligence is increasingly employed to analyze vast datasets, identifying subtle patterns that may indicate biological activity. These technological advances are expanding humanity's reach, increasing the likelihood that the first evidence of extraterrestrial life will be discovered within the coming decades. The panspermia hypothesis adds another fascinating dimension to the search for life. If life can travel between planets via comets, asteroids, or interstellar dust, then Earth may not be unique. Life may have originated elsewhere and seeded our planet, or Earth life may have traveled to other worlds. In this scenario, life is a universal phenomenon, not a rare accident. It connects planets, star systems, and potentially galaxies into a network of biological exchange, emphasizing the universality of life and the interconnectedness of the cosmos. Psychologically, the search for extraterrestrial life reflects humanity's fundamental curiosity and desire for connection. Looking at the stars and asking, "Are we alone?" is an expression of our need for context and meaning. It drives scientific exploration, inspires art and culture, and fosters collaboration across nations. Even if we never find intelligent beings, the search itself enriches human knowledge, emphasizing both the fragility and the preciousness of life on Earth. Asterisk, even in the absence of discovery, the universe teaches us humility. The silence of the stars may indicate the fragility of intelligent life, or the vastness of space and time that separates civilizations. It may remind humanity of the responsibility to protect life on Earth and to preserve our species long enough to explore the cosmos. Survival, adaptation, and resilience are the hallmarks of life, and they are as relevant to humanity as to any potential extraterrestrial species. Scientific exploration continues at a relentless pace. The James Webb Space Telescope and other upcoming observatories are examining exoplanet atmospheres for signs of life. Mars rovers analyze soil and rock for ancient or extant microbes. Future missions to icy moons and distant worlds aim to penetrate subsurface oceans and analyze plumes for organic compounds. Each step brings humanity closer to answering whether we are alone in the universe. Even subtle discoveries, new chemical patterns, anomalous energy readings, or unexpected geological formations can provide critical evidence of life beyond Earth. Even in the absence of discovery, the universe teaches us humility. The silence of the stars may indicate the fragility of intelligent life, or the vastness of space and time that separates civilizations. It may remind humanity of the responsibility to protect life on Earth and to preserve our species long enough to explore the cosmos. Survival, adaptation, and resilience are the hallmarks of life, and they are as relevant to humanity as to any potential extraterrestrial species. Scientific exploration continues at a relentless pace. The James Webb Space Telescope and other upcoming observatories are examining exoplanet atmospheres for signs of life. Mars rovers analyze soil and rock for ancient or extant microbes. Future missions to icy moons and distant worlds aim to penetrate subsurface oceans and analyze plumes for organic compounds. Each step brings humanity closer to answering whether we are alone in the universe. Even subtle discoveries in unusual chemical patterns, anomalous energy readings, or unexpected geological formations can provide critical evidence of life beyond Earth. The universe may be teeming with life in forms both familiar and alien. Microbes may flourish in oceans beneath ice, complex organisms may roam alien landscapes, and intelligent civilizations may ponder the same existential questions we do. Even if we never meet these species face to face, the act of searching unites humanity in a shared endeavor, expanding knowledge, technology, and understanding. It challenges our assumptions, fuels imagination, and provides a cosmic perspective that has never before been possible. Ultimately, the quest to find life elsewhere is also a quest to understand ourselves. It asks what it means to be alive, to be intelligent, and to survive. It reminds us that life on Earth is both rare and precious, demanding stewardship, foresight, and wisdom. Whether we find alien microbes, complex life, or intelligent beings, the discovery will redefine humanity's place in the cosmos. It is a reminder that the universe is vast, ancient, and full of possibilities, an invitation to explore, learn, and marvel at the wonder of existence itself. As humanity continues to peer into the depths of space, each discovery reshapes the way we think about life, intelligence, and the nature of the universe itself. The increasing number of exoplanets discovered in habitable zones suggests that Earth-like conditions may not be as rare as once assumed. Some of these planets are slightly larger than Earth, potentially giving them stronger gravity and thicker atmospheres, while others orbit stars smaller and cooler than the Sun, providing long periods of stability for life to develop. Even planets that seem inhospitable at first glance may possess hidden niches where life could exist, protected from harsh surface conditions by subsurface oceans, thick ice layers, or geothermal activity. These discoveries force us to consider life in ways that go far beyond Earth's familiar environments. The resilience of life on Earth provides a blueprint for understanding its potential elsewhere. Microorganisms, often considered the simplest forms of life, demonstrate incredible adaptability. Some survive extreme radiation, freezing temperatures, or complete dehydration, only to resume metabolic activity when conditions improve. Organisms thriving in hydrothermal vents deep beneath the ocean floor do not rely on sunlight at all but extract energy from chemical reactions. If life on Earth can adapt to such extremes, it becomes conceivable that life could flourish in environments that would appear hostile or uninhabitable to humans. This expands the definition of habitability and informs the search for extraterrestrial species. One of the most intriguing possibilities is the existence of life beneath icy moons. Europa, one of Jupiter's moons, is believed to harbor a vast liquid water ocean beneath its frozen crust. Warmed by tidal forces from Jupiter's gravitational pull, Similarly, Enceladus, orbiting Saturn, ejects plumes of water and organic molecules into space, suggesting a subsurface environment capable of sustaining life. Future missions aim to analyze these plumes directly, searching for microbial life, or even evidence of more complex organisms. The discovery of life in such extreme environments would demonstrate that biology is not confined to Earth-like planets, but can arise wherever the chemistry and energy sources permit it. Beyond our solar system, the detection of biosignatures in exoplanet atmospheres represents a major frontier. Oxygen, methane, and other chemical compounds can serve as indicators of biological activity, particularly when observed in combinations that are difficult to explain through non-biological processes. Advanced telescopes now allow astronomers to study these atmospheres in detail, identifying potential markers of life across vast distances. The first confirmed detection of such a biosignature would be revolutionary, proving that life exists elsewhere and opening an entirely new field of comparative exobiology. Intelligence adds yet another layer of complexity to this search. On Earth, intelligence is rare, appearing only in a handful of species capable of complex thought, tool use, and social organization. Human civilization represents a unique combination of cognitive ability, culture, and technology. Even if life is widespread, intelligence may remain rare, constrained by evolutionary pressures and the contingencies of natural selection. This possibility complicates the search for extraterrestrial civilizations and emphasizes the significance of the Fermi paradox. If intelligent life is possible, why have we not yet observed evidence of it? Several hypotheses attempt to resolve this paradox. Some suggest that civilizations inevitably self-destruct before achieving interstellar communication, falling victim to environmental collapse, warfare, or technological mismanagement. Others propose that advanced species deliberately avoid contact with emerging civilizations, preserving a natural evolutionary trajectory. Yet another possibility is that intelligent life is abundant but communicates in ways that humans cannot detect, using technologies that surpass our current understanding of physics. Each scenario carries implications for humanity, challenging our assumptions about survival, technology, and the nature of intelligence. Ethical considerations are equally important. Discovering extraterrestrial life, whether microbial or intelligent, raises moral questions about interaction, preservation, and stewardship. Planetary protection protocols are designed to prevent contamination between Earth and other worlds, ensuring that alien ecosystems remain pristine and that Earth is not exposed to unknown pathogens. If intelligent life is encountered, the stakes become higher. How should humanity communicate, if at all? What responsibilities do we have toward alien civilizations, and how do we avoid harming them? These questions require careful consideration, global cooperation, and ethical foresight. The cultural impact of discovering life beyond Earth would be profound. Religions and philosophies may need to reinterpret doctrines in light of new evidence. Societies could shift toward a broader, cosmic perspective, recognizing humanity as a single species on a fragile planet, rather than the center of creation. At the same time, fear and uncertainty may provoke resistance, conflict, or denial. Psychological responses to such a discovery could range from awe and wonder to anxiety and existential dread. The impact would extend far beyond the scientific community, influencing art, literature, philosophy, and every facet of human culture. Technology continues to expand the possibilities for discovery. Robotic missions to Mars, Europa, Enceladus, and Titan are designed to explore environments where life may exist, probing subsurface oceans, analyzing organic molecules, and identifying potential biosignatures. Advanced telescopes and instruments allow astronomers to detect exoplanets, characterize their atmospheres, and identify chemical markers of life from light years away. Artificial intelligence is increasingly used to sift through massive amounts of data, recognizing patterns that might otherwise go unnoticed. Each technological advancement brings humanity closer to answering the question of whether we are alone. The panspermia hypothesis adds a fascinating layer to our understanding of life's potential distribution. If life can travel between planets via comets, asteroids, or interstellar dust, Earth may not be unique in hosting biology. Life may have originated elsewhere and seeded our planet, or Earth life may have traveled to other worlds. This idea implies that life is not a rare accident, but a cosmic phenomenon, connecting planets, solar systems, and possibly entire galaxies in a web of biological exchange. Understanding the mechanisms of panspermia could transform our view of life from a local phenomenon to a universal one. Psychologically, the search for extraterrestrial life reflects a fundamental human desire for context and connection. Gazing at the night sky, asking whether we are alone, is an expression of curiosity, imagination, and the drive to understand our place in the cosmos. This drive has motivated exploration, scientific advancement, and philosophical inquiry throughout history. Even if humanity never encounters intelligent life, the search itself enriches knowledge, fosters global cooperation, and reinforces the fragility and preciousness of life on Earth. The absence of evidence thus far also carries lessons. The silence of the cosmos may indicate that intelligent civilizations are rare, isolated, or transient. It may highlight the fragility of life and intelligence and underscore the responsibility of humanity to safeguard its own existence. Observing the potential fragility of life elsewhere reminds us that survival is neither guaranteed nor trivial. Adaptation, resilience, and foresight are critical for the longevity of our species. Scientific exploration continues relentlessly. Observatories like the James Webb Space Telescope and upcoming instruments such as the Extremely Large Telescope enable detailed studies of exoplanet atmospheres and surfaces. Mars rovers analyze soil, rock, and ice for evidence of ancient or extant microbial life. Robotic probes targeting icy moons aim to penetrate subsurface oceans and examine plumes for organic compounds. Even subtle discoveries, unexplained chemical anomalies, energy patterns, or geological formations can provide crucial evidence of extraterrestrial life. Each mission, observation, and experiment moves humanity closer to answering one of the most profound questions in science. The universe may be filled with life, from microscopic organisms thriving beneath icy shells to complex organisms on distant exoplanets, and potentially intelligent civilizations capable of contemplating their existence. Even if direct contact remains improbable due to vast distances, the act of searching unites humanity in a shared pursuit, expanding knowledge, technology, and understanding. It challenges assumptions, fuels imagination, and provides a cosmic perspective that emphasizes both humility and curiosity. Ultimately, the quest to discover extraterrestrial life is also a journey of self-discovery. It asks fundamental questions about survival, intelligence, and the nature of existence. It highlights the uniqueness and fragility of life on Earth and compels humanity to consider its responsibilities toward itself and the cosmos. Whether life beyond Earth is microbial, complex, or intelligent. The discoveries will redefine humanity's understanding of its place in the universe. The search is as much about looking outward as it is about understanding ourselves, reinforcing the profound wonder and significance of life itself. The search for life beyond Earth has also transformed our understanding of what it means to be a planet capable of supporting life. Earth itself is a product of precise conditions: the right distance from the Sun, a protective magnetic field, tectonic activity, a stable atmosphere, and abundant liquid water. Even small variations in these factors could have prevented life from emerging. This recognition has prompted scientists to examine the delicate balance required for habitability and to consider whether similar balances exist elsewhere. The concept of the habitable zone is only the beginning. Subsurface, oceans, tidal heating, atmospheric composition, and chemical energy sources all expand the range of environments in which life might exist. Moons and dwarf planets, often overlooked in the past, have become prime targets for astrobiology. Europa and Enceladus, with their subsurface oceans, exemplify worlds where life could exist independently of sunlight. The discovery of organic compounds in Enceladus's plumes demonstrates that the raw materials for life are not confined to Earth. Titan, with its methane and ethane lakes, suggests that entirely different biochemistries could evolve under conditions previously considered inhospitable. Studying these bodies forces us to reconsider the universality of water-based life and the flexibility of biological systems. Life may adapt to environments far removed from terrestrial norms, and these adaptations could reveal principles of biology that we have never imagined. Exoplanet research continues to push the boundaries of what is possible. Thousands of exoplanets have been discovered in habitable zones, and the next generation of telescopes promises to examine their atmospheres in detail. Oxygen, methane, nitrous oxide, and other gases may serve as biosignatures, revealing biological processes from light years away. The detection of a single biosignature could confirm that life exists beyond Earth, while multiple correlated signals could provide stronger evidence and even suggest active ecosystems. This approach turns the cosmos into a laboratory for comparative biology, allowing scientists to test theories about life's origin, evolution, and potential universality. Intelligence, particularly technological intelligence, is another frontier. On Earth, intelligence is a rare outcome of evolution, appearing in only a few species capable of complex problem-solving and communication. Humans represent a unique combination of cognitive ability, cultural complexity, and technological innovation. Even if life is widespread, intelligent life may remain rare, constrained by evolutionary contingencies. The Fermi paradox underscores this uncertainty. If intelligent life is probable, why have we not observed it? Solutions range from the possibility that civilizations self-destruct before achieving interstellar communication to the notion that advanced species deliberately avoid contact. Other hypotheses suggest that extraterrestrial intelligence may communicate in ways beyond our current detection capabilities, such as neutrino streams, quantum entanglement, or other unknown technologies. Ethical considerations accompany the potential discovery of life. Planetary protection protocols are designed to prevent contamination between Earth and other worlds, preserving alien ecosystems and protecting Earth from potential pathogens. If intelligent life is encountered, ethical questions become even more complex. How should humanity communicate, interact, and respect extraterrestrial beings? What responsibilities do we have to ensure their welfare, and what precautions are necessary to safeguard humanity? These questions highlight the intersection of science, morality, and foresight, emphasizing that the search for life is not only a scientific endeavor but also an ethical one. The cultural ramifications are profound. Humanity has long defined itself as unique, but the discovery of extraterrestrial life challenges this perception. Religions may reinterpret doctrines, philosophies may expand to include cosmic perspectives, and societies may shift toward global unity. Conversely, fear of the unknown could provoke anxiety, conflict, or denial. Psychological responses would vary widely, ranging from awe and inspiration to existential dread. The discovery of life beyond Earth would permeate every aspect of culture, influencing art, literature, philosophy, and social structures. Technology remains central to this quest. Robotic missions to Mars, Europa, Enceladus, and Titan aim to probe subsurface oceans, analyze plumes, and detect organic molecules. Space telescopes examine exoplanet atmospheres for biosignatures, while AI algorithms sift through massive datasets, identifying patterns that might indicate life. Each technological advance increases the probability of discovery and enhances our understanding of where and how life may exist. The integration of human ingenuity with cutting-edge technology represents a critical factor in humanity's search for cosmic neighbors. The panspermia hypothesis provides an intriguing lens through which to view life's distribution. If life can travel between planets via comets, asteroids, or interstellar dust, Earth may not be unique. Life could have originated elsewhere and seeded our planet, or terrestrial life could have spread to other worlds. This idea suggests that life is a cosmic phenomenon, linking planets and star systems across vast distances. Understanding panspermia not only informs our search for life, but also reframes our understanding of biology as a universal process, rather than an isolated accident. The search for life also reflects fundamental human psychology. Gazing at the stars and asking, "Are we alone?" is an expression of curiosity, imagination, and the desire for context. It drives exploration, fuels scientific inquiry, and inspires cultural development. Even in the absence of discovery, the pursuit enriches humanity by fostering cooperation, advancing technology, and emphasizing the value of life on Earth. The search for extraterrestrial life, therefore, is as much a reflection of humanity's inner quest for understanding as it is a scientific endeavor. The absence of evidence, to date, highlights the fragility and rarity of life. The silence of the cosmos may indicate that intelligent civilizations are isolated, transient, or rare. This recognition underscores the importance of preserving Earth's biosphere and safeguarding human civilization. Adaptation, resilience, and foresight are crucial for long-term survival. Humanity may be among the first species to achieve interstellar awareness, and with that awareness comes the responsibility to ensure continuity. Scientific exploration continues relentlessly. Observatories such as the James Webb Space Telescope, the Extremely Large Telescope, and future instruments enable detailed studies of exoplanets and their atmospheres. Mars rovers continue to analyze soil, rock, and ice for signs of past or present microbial life. Probes targeting icy moons aim to penetrate subsurface oceans and examine plumes for organic compounds. Even subtle anomalies, unexpected chemical signatures, energy patterns, or geological formations could indicate extraterrestrial life. Each mission brings humanity closer to answering one of the most profound questions in science. Are we alone? The universe may be teeming with life. From microscopic organisms beneath icy shells to complex life forms on distant worlds, and possibly intelligent civilizations contemplating their own existence. Even if direct contact remains improbable, the act of searching unites humanity, expands knowledge, and provides a cosmic perspective. It challenges assumptions, fuels imagination, and encourages a deeper understanding of life, intelligence, and existence. Ultimately, the quest to discover life beyond Earth is a journey of self-discovery. It asks what it means to survive, to be intelligent, and to understand our place in the universe. It emphasizes the uniqueness and fragility of life on Earth and the responsibilities humanity holds. Whether life elsewhere is microbial, complex, or intelligent, each discovery will redefine humanity's understanding of existence. The search is both outward and inward, revealing not only the possibilities of the cosmos but the depths of human curiosity, resilience, and wonder. As humanity continues to explore the cosmos, one of the most profound insights is the realization that life may take forms and exist under conditions that were once considered impossible. On Earth, life demonstrates remarkable resilience and adaptability, thriving in extreme heat, cold, pressure, radiation, and even complete darkness. Microbial communities exist in boiling hydrothermal vents, frozen Antarctic lakes, deep within the Earth's crust, and in highly acidic or alkaline environments. These extremophiles provide a blueprint for understanding how life could arise and survive elsewhere in the universe. Their existence suggests that the emergence of life may not require the precise, Earth-like conditions previously assumed, but rather any environment that offers chemical energy and the possibility for self-replicating molecules. This perspective radically broadens the concept of habitability. Planets or moons previously dismissed as too extreme may, in fact, harbor life. Europa's subsurface ocean, insulated by a thick layer of ice and heated by tidal forces from Jupiter, is a prime candidate for microbial ecosystems independent of sunlight. Enceladises, plumes eject water, salts, and organic molecules, offering a tantalizing glimpse into potentially habitable environments beneath its icy crust. Titan, with lakes of liquid methane and ethane, demonstrates that alternative biochemistries might exist, challenging the assumption that life must be water-based. Each of these environments exemplifies the principle that life, once it arises, will adapt to the available energy sources, chemical composition, and environmental constraints. Exoplanet research continues to push the boundaries of discovery. Thousands of planets have been detected orbiting stars beyond our solar system, with many situated in their star's habitable zone. While some are Earth-like in size and composition, others are super-Earths or mini-Neptunes, offering a spectrum of conditions under which life might exist. Observations of their atmospheres using spectroscopy allow scientists to search for biosignatures such as oxygen, methane, and other chemical markers indicative of biological activity. Detecting these signatures could provide evidence of life without requiring direct exploration, transforming astronomy into a tool for universal biology. Intelligence, particularly technological intelligence, presents additional complexity. Human intelligence, capable of language, abstract reasoning, and technological innovation, is rare among Earth's species. While dolphins, crows, and octopuses demonstrate remarkable cognitive abilities, they have not developed civilizations. The emergence of intelligent life elsewhere may be similarly constrained by evolutionary pressures, environmental factors, and random events. The Fermi paradox arises from this conundrum. If intelligent life is possible, why have we not observed it? Potential explanations include self-destruction of civilizations, deliberate avoidance of contact, or communication methods beyond human detection. Ethical considerations are central to the search for extraterrestrial life. Planetary protection protocols aim to prevent contamination of other worlds and protect Earth from unknown organisms. Should intelligent life be discovered, ethical questions multiply. How should humanity interact, communicate, or even acknowledge alien beings? These dilemmas require foresight, cooperation, and global consensus, highlighting that the search for life is both a scientific and moral endeavor. Cultural and societal impacts of discovering life would be immense. Humanity has long considered itself unique, but extraterrestrial life would challenge this assumption. Religions, philosophies, and social structures would be forced to adapt, potentially leading to a more unified global perspective. Conversely, fear and uncertainty could provoke societal anxiety or conflict. The psychological implications are profound, influencing art, literature, and the collective imagination. The discovery of life, particularly intelligent life, would reshape human culture in ways difficult to predict. Technological advances remain crucial. Robotic missions to Mars, Europa, Enceladus, and Titan aim to sample surfaces, probe subsurface oceans, and analyze organic compounds. Space telescopes examine exoplanet atmospheres for biosignatures, while artificial intelligence sifts through enormous datasets to identify subtle patterns that may indicate life. Each technological improvement enhances humanity's ability to detect and understand life beyond Earth, bridging the gap between imagination and observation. The panspermia hypothesis adds a fascinating dimension. If life can travel between planets via comets, asteroids, or interstellar dust, Earth may not be unique. Life might have originated elsewhere and seeded our planet, or Earth life could have spread to other worlds. This idea reframes biology as a cosmic process rather than a rare accident, suggesting that life could be interconnected across solar systems and galaxies. Understanding panspermia informs both the search for life and our understanding of how biology operates on a universal scale. Human curiosity and psychology drive this quest. Looking to the stars and asking, "Are we alone?" reflects a fundamental need for context and connection. This curiosity has fueled exploration, scientific progress, and cultural development for centuries. Even without direct evidence of life, the search enriches humanity by fostering cooperation, advancing technology, and emphasizing the fragility and value of life on Earth. The pursuit itself is as meaningful as the discovery, providing perspective and inspiring wonder. The apparent absence of evidence carries lessons. The silence of the cosmos may indicate that intelligent civilizations are rare, isolated, or transient. This possibility underscores humanity's responsibility to preserve life on Earth and ensure the longevity of human civilization. Adaptation, resilience, and foresight are essential for survival. Humanity may be among the first species to attain interstellar awareness. With the duty to safeguard both knowledge and existence, scientific exploration continues at a rapid pace. Telescopes like James Webb and upcoming instruments such as the Extremely Large Telescope allow detailed study of exoplanet atmospheres. Mars rovers analyze soil, rock, and ice for ancient or extant microbial life. Robotic probes target icy moons to penetrate subsurface oceans and examine plumes for organic molecules, even subtle anomalies, unexpected chemical patterns, geological formations, or energy emissions can provide clues of extraterrestrial life. Each mission advances humanity closer to answering the profound question: are we alone in the universe? The universe may harbor life across a spectrum, from microscopic organisms beneath ice to complex organisms on distant exoplanets and potentially intelligent civilizations. Even without direct contact, the pursuit of understanding unites humanity, expands knowledge, and provides a cosmic perspective. It challenges assumptions, fuels imagination, and encourages reflection on the nature of life, intelligence, and existence. Ultimately, the quest for extraterrestrial life is also a journey of self-discovery. It asks what it means to survive, to be intelligent, and to exist within a vast universe. It emphasizes the uniqueness and fragility of life on Earth, as well as humanity's responsibility for its preservation. Whether life elsewhere is microbial, complex, or intelligent, each discovery will redefine humanity's understanding of its place in the cosmos. The search is both outward and inward, revealing not only the possibilities of life in the universe, but also the depths of human curiosity, resilience, and wonder. The implications of discovering life extend even further when considering the potential for technological civilizations. If advanced intelligent species exist, they may have developed technologies far beyond human comprehension. Their communication methods might exploit principles of physics unknown to us, rendering their signals undetectable with current instruments. Detecting such civilizations would not only confirm that intelligent life exists, but also provide insights into the trajectory of technological evolution, societal stability, and the potential longevity of civilizations. Understanding these factors could guide humanity's own development, offering cautionary tales or inspiring progress. Furthermore, the interaction between biological life and planetary environments becomes a key area of study. Life modifies its surroundings. Earth's atmosphere, for example, evolved through the metabolic activity of microorganisms over billions of years. Recognizing similar interactions on other worlds could indicate the presence of life, even if direct observation is impossible. Studying these planetary biosignatures allows scientists to infer ecosystems' existence, diversity, and dynamics, highlighting that life leaves detectable imprints on its environment. The pursuit of extraterrestrial life also shapes humanity's approach to space exploration. Rather than merely seeking resources or territory, missions increasingly focus on understanding ecosystems, preserving potential habitats, and investigating life's origin and evolution. Ethical and environmental considerations become intertwined with scientific objectives, reflecting a mature approach to cosmic exploration. This perspective emphasizes stewardship, humility, and responsibility, acknowledging that the discovery of life would transform humanity's relationship with the universe. Education and public engagement play crucial roles as well. Humanity's fascination with extraterrestrial life inspires scientific literacy, curiosity, and innovation. Public interest drives funding, international cooperation, and the development of new technologies. By involving society in the search for life, scientists cultivate a shared sense of purpose and wonder, emphasizing that the quest for knowledge belongs to all of humanity. In sum, the search for life beyond Earth is a multifaceted endeavor that combines science, ethics, culture, and psychology. It challenges humanity to expand its understanding, embrace responsibility, and confront fundamental questions about existence. Life may exist in forms and environments vastly different from our own, yet its discovery, microbial, complex, or intelligent, would reshape our understanding of the universe. The pursuit itself enriches humanity, highlighting both our potential and our responsibilities. The universe is vast, ancient, and teeming with possibilities. Microbial life may thrive beneath ice, complex organisms may inhabit distant worlds, and intelligent civilizations may ponder their own existence far from our view. Humanity's ongoing exploration represents a profound commitment to understanding life, intelligence, and the cosmos. Each discovery, whether direct or inferred, expands knowledge, challenges assumptions, and inspires. Ultimately, the search for extraterrestrial life is a testament to human curiosity, resilience, and the enduring desire to connect with the universe beyond our small, fragile planet. The vastness of the universe, with its billions of galaxies, each containing billions of stars, presents both opportunity and challenge in the search for life. Every star potentially hosts planets, and among these, some may fall within habitable zones where conditions are favorable for life as we understand it. However, the true measure of habitability extends beyond mere distance from a star. Planetary atmosphere, magnetic fields, chemical composition, presence of liquid solvents, and geological activity all contribute to a planet's ability to sustain life. Earth itself serves as the template. Its stable climate, abundant liquid, water, and protective magnetosphere enabled life to emerge and evolve over billions of years. Understanding these factors allows scientists to identify exoplanets that might harbor life, even if they differ significantly from Earth. On Earth offer invaluable lessons about the resilience and adaptability of life. Organisms survive in environments previously considered hostile to biology: superheated hydrothermal vents, sub-zero Antarctic lakes, acidic hot springs, and the crushing pressures of the deep ocean floor. Some microbes can endure extreme radiation, complete desiccation, or prolonged absence of oxygen, only to resume metabolic activity when favorable conditions return. These examples suggest that life may exist in forms and places far beyond our current imagination. If life could adapt to such extremes on Earth, then it is conceivable that life could thrive in icy oceans beneath the surface of moons like Europa, or in Enceladus, or even in the hydrocarbon lakes of Titan. Exoplanetary research has expanded our understanding of potential life-bearing worlds. Thousands of exoplanets have been confirmed, many located within the so-called habitable zones of their stars. Some are Earth-like in size and composition, while others are super-Earths or ocean worlds. These diverse environments challenge scientists to expand the definition of habitability beyond Earth-centric parameters. Using advanced spectroscopy, researchers analyze exoplanet atmospheres for biosignatures, chemical markers such as oxygen, methane, and carbon dioxide in combinations unlikely to arise from non-biological processes. The detection of such signatures would provide compelling evidence of extraterrestrial life and revolutionize our understanding of biology on a cosmic scale. Intelligence adds another layer of complexity to this search. On Earth, intelligence evolved in only a few species capable of complex thought, communication, and tool use. Humans, with their unique combination of cognitive ability and cultural development, are the only species known to create technology and civilizations. The emergence of intelligent life elsewhere may be rare, contingent on a long series of evolutionary events. The Fermi paradox: why If intelligent life is probable, we have not observed it remains a central question. Possible solutions include the self-destruction of civilizations, intentional avoidance of contact, or communication methods beyond human detection, such as quantum or neutrino-based signals. Each possibility challenges assumptions about the evolution, survival, and detectability of intelligence. Ethics play a critical role in the search for life. Planetary protection protocols exist to prevent the contamination of other worlds with Earth organisms and to protect Earth from potential extraterrestrial microbes. The discovery of intelligent life would multiply these ethical concerns. Questions of communication, interaction, and preservation would require global collaboration, ethical foresight, and long-term planning. Humanity must consider the consequences of its actions, ensuring that exploration and contact are conducted responsibly. The search for life, therefore, encompasses not only science, but also morality and the stewardship of both Earth and the cosmos. Cultural implications of discovering life would be transformative. Humanity has long regarded itself as unique, yet extraterrestrial life would challenge this perspective. Religions, philosophies, and social structures might adapt to a cosmic context, potentially fostering unity or provoking societal anxiety. The psychological impact of discovering life, particularly intelligent life, would be profound, influencing art, literature, education, and collective imagination. It could inspire a renewed sense of purpose or, conversely, evoke fear and uncertainty. The discovery of extraterrestrial life is therefore not only a scientific milestone, but a cultural and existential one. Technological advancement is central to the quest for extraterrestrial life. Robotic missions to Mars, Europa, Enceladus, and Titan aim to explore subsurface oceans, analyze plumes, and detect organic compounds. Space telescopes examine exoplanet atmospheres for biosignatures, while artificial intelligence helps process enormous datasets, identifying subtle indications of life that might otherwise be missed. Each technological innovation brings humanity closer to answering the question of whether life exists beyond Earth, demonstrating the interplay of curiosity, ingenuity, and scientific rigor. The panspermia hypothesis adds another dimension to the search. Life may be transferable between planets via comets, asteroids, or interstellar dust. If true, Earth may not be unique. Life could have originated elsewhere and seeded our planet, or terrestrial life could have spread to other worlds. This concept transforms our understanding of biology, suggesting it may be a cosmic phenomenon rather than an isolated occurrence. Panspermia emphasizes the interconnectedness of life, linking planets, solar systems, and potentially entire galaxies in a web of biological exchange. Human psychology drives the quest for life beyond Earth. Gazing at the stars and asking, "Are we alone?" reflects a deep-seated need for connection, context, and understanding. This curiosity motivates exploration, fuels scientific discovery, and inspires cultural growth. Even without direct evidence, the pursuit enriches humanity by fostering cooperation, advancing technology, and emphasizing the value of life on Earth. The search for extraterrestrial life is as much an exploration of the universe as it is a reflection of humanity's inner desire for knowledge and understanding. The apparent absence of evidence also teaches important lessons. The silence of the cosmos may suggest that intelligent civilizations are rare, isolated, or transient. This recognition underscores the importance of safeguarding life on Earth and ensuring the continuity of human civilization. Adaptation, resilience, and foresight are essential for survival. Humanity may be among the first species to attain interstellar awareness, carrying the responsibility to preserve knowledge, culture, and life itself. Scientific exploration continues at an unprecedented pace. Observatories, such as the James Webb Space Telescope, the Extremely Large Telescope, and next-generation instruments enable detailed studies of exoplanetary atmospheres. Mars rovers analyze soil, rock, and ice for microbial fossils or extant life. Probes targeting icy moons aim to penetrate subsurface oceans and analyze plumes for organic molecules. Even subtle anomalies, unexplained chemical signatures, geological formations, or energy emissions could indicate extraterrestrial life. Each mission advances humanity closer to answering the fundamental question of whether life exists elsewhere in the universe. The universe may be home to life across a spectrum, from microorganisms beneath ice sheets to complex organisms on distant worlds, and potentially intelligent civilizations capable of pondering their own existence. Even if direct contact is unlikely due to vast distances, the pursuit of knowledge unites humanity, expands understanding, and provides a cosmic perspective. It challenges assumptions, fuels imagination, and promotes a deeper comprehension of life, intelligence, and existence itself. Ultimately, the quest for extraterrestrial life is inseparable from humanity's quest for self-understanding. It asks what it means to survive, to be intelligent, and to exist in a vast universe. It emphasizes the uniqueness and fragility of life on Earth and humanity's responsibility for its preservation. Whether life elsewhere is microbial, complex, or intelligent, its discovery will redefine humanity's understanding of the cosmos. The search is both outward and inward, revealing not only the possibilities of life beyond Earth, but also the depths of human curiosity, resilience, and wonder. As humanity progresses, the implications of discovering life, especially intelligent life, become ever more significant. Advanced civilizations may possess technologies beyond human comprehension, communicating via methods undetectable by current instruments. Understanding such civilizations could reveal insights into the longevity of technological societies, strategies for survival, and the potential trajectories of intelligence. Even microbial life elsewhere provides lessons about biology, adaptation, and the universality of life's principles. Planetary ecosystems themselves can serve as indirect indicators of life. On Earth, biology has dramatically reshaped the environment, from the composition of the atmosphere to the formation of soil and the cycling of nutrients. Recognizing similar biosignatures on other worlds could indicate the presence of life even without direct observation. The study of planetary biosignatures thus becomes a powerful tool for detecting extraterrestrial life, highlighting the interplay between organisms and their environment across the cosmos. The search also informs humanity's approach to space exploration. Rather than treating celestial bodies merely as resources, missions increasingly emphasize understanding ecosystems, preserving potential habitats, and investigating life's origin and evolution. Ethical and environmental considerations are integral, reflecting a mature approach to exploration. Stewardship, humility, and responsibility become as important as discovery, ensuring that the search for life enhances understanding without causing harm. Education and public engagement amplify the significance of this quest. Humanity's fascination with extraterrestrial life inspires curiosity, scientific literacy, and innovation. Public interest drives funding, international collaboration, and the development of new technologies. Engaging society in the search fosters a shared sense of purpose and wonder, reinforcing that the pursuit of life beyond Earth is a collective endeavor. In sum, the search for life beyond Earth encompasses science, ethics, culture, and human psychology. It challenges humanity to expand understanding, embrace responsibility, and confront profound questions about existence. Life may exist in forms and environments vastly different from Earth. Yet, its discovery, microbial, complex, or intelligent, would redefine humanity's understanding of the universe. The pursuit enriches knowledge, emphasizes the value of life, and highlights humanity's potential and responsibilities. The cosmos is vast, ancient, and full of possibilities. Life may thrive beneath icy shells, in distant oceans, or on alien planets with conditions unlike anything on Earth. Intelligent civilizations may contemplate existence far beyond our perception. Humanity's exploration reflects a profound commitment to understanding life, intelligence, and the universe. Each discovery, whether direct or inferred, expands knowledge, challenges assumptions, and inspires awe. The search for life is a testament to human curiosity, resilience, and the enduring desire to understand the cosmos beyond our fragile planet. The possibility that we are not alone in the universe compels humanity to rethink its place in the cosmic order. Our perspective, once centered exclusively on Earth, expands as we consider the vast number of potentially habitable worlds. Each planet, moon, and exoplanetary system offers unique conditions for life to emerge, evolve, and adapt. Some worlds may host microbial ecosystems beneath icy crusts, while others may support complex life on surface oceans or landmasses. The universe may be far richer biologically than humans have ever imagined, and the quest to uncover these possibilities drives scientific exploration forward. Life, as we know it, relies on the interplay of chemistry, energy, and environment. Yet the diversity of life on Earth suggests that nature is capable of immense flexibility. Microorganisms survive in boiling acidic springs, frozen tundras, deep ocean trenches, and high radiation zones. Some species can endure years without water or oxygen, only to resume metabolic activity when favorable conditions return. This adaptability implies that life could exist under a range of conditions vastly different from Earth's, thriving wherever chemical energy, liquid solvents, and stable environments are present. Consequently, planets and moons once dismissed as inhospitable are now considered promising targets for the search for life. Icy moons, such as Europa and Enceladus, exemplify environments where life might flourish in extreme isolation. Europe's subsurface ocean is kept liquid by tidal heating from Jupiter's gravitational pull, while Enceladus ejects plumes of water and organic molecules into space, hinting at potential ecosystems beneath its icy crust. Titan's methane and ethane lakes suggest the possibility of life using alternative biochemistries. Investigating these bodies requires sophisticated robotics and instrumentation capable of probing beneath ice layers, analyzing chemical compositions, and detecting organic molecules. Each mission contributes vital knowledge about how life might persist in extreme conditions and informs the broader search across the cosmos. Exoplanet studies further expand our understanding. Thousands of planets orbit stars beyond our solar system, many located in habitable zones where liquid water could exist. Some are Earth-like, others are super-Earths, mini-Neptunes, or ocean worlds, offering diverse environments for life to develop. scientists employ advanced spectroscopy to study atmospheric composition, searching for biosignatures such as oxygen, methane, and other compounds indicative of biological activity. Detecting these signals from light years away could confirm that life exists beyond Earth, providing the first direct evidence that biology is a universal phenomenon rather than an isolated occurrence. Intelligence introduces an additional layer of complexity. While life may be widespread, intelligence capable of civilization appears rare. Humans are unique among Earth's species, possessing the cognitive ability to create technology, manipulate environments, and form complex societies. The Fermi paradox questions why, if intelligent life is probable, we have yet to observe it. Explanations range from the self-destruction of civilizations to the possibility that advanced species intentionally avoid contact, or that they communicate using methods beyond human comprehension, such as quantum entanglement or exotic energy-based signals. Understanding these possibilities informs humanity's own technological trajectory and philosophical perspective. Ethical considerations are paramount. Planetary protection protocols aim to prevent contamination of extraterrestrial environments and protect Earth from potential alien pathogens. Should intelligent life be discovered, ethical questions multiply. How should humanity communicate, interact, or respect alien civilizations? These dilemmas demand global cooperation, foresight, and moral responsibility. The search for life is therefore not solely a scientific enterprise. It is a profound exercise in stewardship, emphasizing the importance of ethical exploration and the preservation of ecosystems both terrestrial and extraterrestrial. The cultural ramifications of discovering life are immense. Humanity's perception of uniqueness would be challenged, prompting potential re-evaluation of religious, philosophical, and social frameworks. Societies might unite in a shared cosmic perspective or experience anxiety and conflict driven by fear of the unknown. The discovery of life, particularly intelligent life, would inspire art, literature, and education, reshaping human culture in ways that are difficult to predict. This profound encounter with the broader universe would transform not only science, but the collective human imagination. Technological advancement remains critical in this endeavor. Robotic missions to Mars, Europa, Enceladus, and Titan aim to probe subsurface oceans, analyze plumes, and detect organic compounds. Space telescopes study exoplanetary atmospheres for biosignatures, while artificial intelligence helps sift through enormous datasets, recognizing subtle signals that might indicate life. Each technological improvement brings humanity closer to discovering extraterrestrial life and understanding its nature. Technology extends our reach, allowing us to study worlds far beyond our solar system and to detect signs of life invisible to the naked eye. The panspermia hypothesis adds a fascinating dimension. Life may traverse the cosmos via comets, asteroids, or interstellar dust, suggesting that Earth may not be unique in harboring life. Life could have originated elsewhere and seeded our planet, or Earth life could have spread to other worlds. This possibility implies that life is a universal phenomenon, not merely a product of earthly conditions. Understanding panspermia broadens our view of biology, emphasizing that life may be interconnected across vast distances, linking planets, solar systems, and potentially entire galaxies. Human curiosity drives the search for life. The question, "Are we alone?" reflects a profound need for understanding, connection, and context. This inquiry motivates exploration, scientific advancement, and cultural growth. Even in the absence of definitive discovery, the pursuit enriches humanity by fostering collaboration, technological innovation, and appreciation for the fragility and uniqueness of life on Earth. The search for extraterrestrial life, therefore, serves both a scientific and existential purpose, reflecting humanity's desire to comprehend its place in the universe. The silence of the cosmos offers lessons in humility. The apparent absence of detectable intelligent civilizations may indicate that they are rare, isolated, or transient. This realization underscores the importance of preserving Earth's biosphere and ensuring the longevity of human civilization. Adaptation, foresight, and resilience are essential. Humanity may be among the first species to attain interstellar awareness, bearing the responsibility to safeguard both knowledge and life itself. Scientific exploration progresses at an unprecedented pace. Telescopes such as James Webb, the Extremely Large Telescope, and future instruments enable detailed studies of exoplanetary atmospheres. Mars rovers analyze soil, rock, and ice for evidence of past or present microbial life. Probes targeting icy moons penetrate subsurface oceans and examine plumes for organic compounds. Even subtle anomalies, unexpected chemical signatures, geological formations, or energy emissions can provide critical evidence of extraterrestrial life. Each discovery advances humanity closer to answering the profound question of whether we are alone in the universe. Life may exist across a spectrum, from microorganisms beneath icy crusts to complex organisms on distant exoplanets, and potentially intelligent civilizations capable of reflection and innovation. Even without direct contact, the pursuit of understanding unites humanity, expands knowledge, and fosters a cosmic perspective. It challenges assumptions, inspires imagination, and encourages reflection on the nature of life, intelligence, and existence. Ultimately, the search for extraterrestrial life is inseparable from humanity's quest for self-understanding. It asks what it means to survive, to be intelligent, and to exist within a vast universe. It emphasizes the uniqueness and fragility of life on Earth and the responsibility humans bear for its preservation. Whether life elsewhere is microbial, complex, or intelligent, each discovery will redefine humanity's understanding of existence. The search is both outward and inward, revealing not only the possibilities of life in the universe, but also the depths of human curiosity, resilience, and wonder. As humanity progresses, the implications of discovering intelligent life become particularly profound. Advanced civilizations may employ technologies beyond human understanding, communicating through means currently undetectable. Understanding such civilizations could provide insights into survival strategies, longevity of civilizations, and the evolution of intelligence. Even microbial life elsewhere offers lessons about biology, adaptation, and the universality of life's principles. Studying extraterrestrial life can inform both science and philosophy, revealing patterns and possibilities that reshape human understanding. Planetary ecosystems serve as indirect indicators of life. Life interacts with and modifies its environment. Earth's atmosphere, hydrosphere, and lithosphere were shaped by biological activity over billions of years. Recognizing similar biosignatures elsewhere could indicate the presence of life, even without direct observation. This interplay between organisms and environment highlights the universality of life's influence on planetary systems, guiding scientists in the identification of habitable worlds. The pursuit of life beyond Earth also informs humanity's approach to space exploration. Rather than treating planets as resources, exploration increasingly emphasizes understanding ecosystems, preserving habitats, and investigating the origins and evolution of life. Ethical and environmental considerations are integral, reflecting a mature approach to discovery. Stewardship, humility, and responsibility ensure that exploration enhances understanding without causing harm, acknowledging that the discovery of life transforms humanity's relationship with the cosmos. Education and public engagement amplify the significance of the quest. Humanity's fascination with extraterrestrial life inspires curiosity, literacy, and innovation. Public interest drives funding, collaboration, and technological development. Engaging society in the search fosters a collective sense of purpose, emphasizing that the quest to understand life beyond Earth belongs to all of humanity. In conclusion, the search for life beyond Earth encompasses science, ethics, culture, and human psychology. It challenges humanity to expand understanding, embrace responsibility, and confront profound questions about existence. Life may exist in forms and environments vastly different from Earth, yet its discovery, microbial, complex, or intelligent, would redefine humanity's perspective on the universe. The pursuit enriches knowledge, emphasizes the value of life, and highlights humanity's potential and responsibilities. The cosmos is vast, ancient, and full of possibilities. Life may thrive beneath icy surfaces, in distant oceans, or on alien planets with environments unlike Earth. Intelligent civilizations may contemplate existence far beyond our perception. Humanity's exploration reflects a profound commitment to understanding life, intelligence, and the universe. Each discovery, whether direct or inferred, expands knowledge, challenges assumptions, and inspires awe. The search for life is a testament to human curiosity, resilience, and the enduring desire to understand the cosmos beyond our fragile planet. In the end, whether life is microbial, complex, or intelligent, the universe beckons humanity to explore, learn, and reflect. Our journey across the stars is not merely a quest for discovery, it is a quest to understand ourselves, our origins, and our potential. The cosmos is a mirror, reflecting the boundless curiosity and ingenuity of a species determined to know whether it is alone, and if not, how it connects to the greater web of life that may span the universe. The answer, when it comes, will redefine humanity forever.